use of this IC, which is LM317, which is nothing but an adjustable voltage regulator. Okay, your LM317 is an adjustable voltage regulator where you can get a range of voltages. Right? In the earlier case, we were getting only fixed value. Always I get 5 volt as my output. Now, if I want a range of voltage, say I want from say 3 volt to some 20 volt or from 3 volt to some 15 volt, I want to vary it, then I go for this adjustable voltage regulator, which is nothing but my LM317. So, as per the syllabus of fundamentals of electronics, you also have an experiment on this LM317. Okay, so now how we are, let's see the pin configuration of this. It is also a 3-pin IC like our 7805. This is also a 3-pin IC, and here you can see the pin diagram where 1, 2 and 3. 1 signifies it is the adjustable pin, 2 is your output and 3 is your V-in. So you should be very careful while using this. Generally what happens, first pin will be the input and last will be the output, but that's not so here. The first is an adjustable pin, second is your V out and third is your V in. So please make a note of it. Okay. Otherwise, it's a plastic package like your 7805. This also comes in a plastic package only. So keep the specification facing you, then pin pointing downwards. It's 1, 2 and 3. Adjustable, V out and V in. Now, how can I make it as an adjustable voltage regulator? Basically, this is the setup. I provide my V in. So, V in is given from where? From where does your V in come? Output of filter. Output of filter is nothing but the input to my regulator. So, output of filter is nothing but an unregulated DC, what we are getting. Output of rectifier was a pulsating DC. Now that we had given to a filter where we are having an unregulated DC output. So now that is given as an input to your LM317. So now how I am going to make it as an adjustable one? So it can be made as an adjustable by making use of this R1 and R2 combination. Okay, using this R1 and R2 combination, you can make it programmable or you can make it adjustable. Now the regulated output that comes from this, it's in the range of say 1.25 to 37. Okay, it's not 0. Minimum I'll have a 1.25 volt. So that will be when I have the protect, it is basically to protect it. So the minimum voltage will be 1.25 and maximum I can achieve till say 37 volt. And what is the current rating? The output current rating is 1.5. What was the current rating of our 7805? 1 ampere. Okay, here in this case it is 1.5 amperes. And how is it made adjustable or programmable? It is made adjustable by making use of this R1 and R2 combination. So it includes your current limiting, internal overload protection as well as the thermal protections in this case. Now it is equation, it's governed by an equation. So the equation is, I'll just show it with the diagram. V out is equal to V ref into 1 plus R2 by R1. So V out is the output voltage I get here across the terminals, right? R2 is this resistor and R1 is this resistor. R2 generally we will make it as a potentiometer. We will make it as a variable resistor or a potentiometer, and R1 will be your fixed resistor. And Vref is nothing but the voltage across this point. Okay, so by design this Vref will be equal to 1.25. So my equation will be your V0 is equal to 1.25 into 1 plus R2 by R1. That will be my output voltage. So if I write the equation, I can write it as 1.25 into 1 plus R2 by R1. That will be my equation for my V output voltage. So in this, your R2 is going to be your variable resistor or a potentiometer, and R1 can be the fixed resistor. So what happens when I vary the potentiometer? Naturally, my output voltage will also change. Right? Now, if both of them are going to be the same value, if my R1 and R2 are same value, what will be the output voltage that I will get? Say, my both R1 and R2 are same value. Let's say 2 times your 1.25. So 2 times your 1.25 means I will be getting say 2.5 volts. Okay, so it all depends upon this combination, right? Let's see the data sheet of this also. And here, as per the syllabus, you have an experiment with this LM317, like how you had for your say 7805. Okay, so this is the circuit diagram what you will be doing, and here V in will be provided from the regulated power supply. Now we will be giving the filtered output, whereas in the laboratory when you are doing it for the students, it will be given from your regulated power supply. And like how we did in our say 7805, you have a capacitor in the input side as well as in the output side. So this from the data sheet only the value is taken. In the input side my capacitor is 0.1 microfarad, and in the output side my capacitor value is 1 microfarad, and it is programmable by making use of this combination of R1 and R2. Here the equation, it should be 1.25 into 1 plus R2 by R1. There is a mistake in the print. It's R2 divided by R1. So what you are supposed to do in this particular experiment is, because once you know 7805 and all that, it's very easy to do this also. So you have to vary the resistance basically. You have to vary your R2. So R2, how am I going to vary? I'm going to vary as 100 ohm, 220, 470, 680, 1K like that. And then find out what is going to be my V out practical value. V out practical value, I will just connect a multimeter and then I will find out my output voltage. And V out theoretical, what will I do? I will substitute in this equation. Okay, so let's say I put 100 ohms. So it is 1.25 into 1 plus 100 divided by my R1 is 330. Okay, so 1 plus 220 divided by 330 into 1.25. That will be the theoretical output value. Practically, what do we obtain? You just make use of your multimeter, note down the value and then record it here. Similarly, when I go for say 680 ohm, so if I substitute 1.25 into 1 plus 680 by 330. Okay, so whatever value you get, that will be the theoretical output. Practically, you measure using your DMR. So this is the experiment that you have to perform at the center if you are allocated this subject. And here in this manual only I have given the link for the your data sheet also. Okay, otherwise also it will be uploaded as part of your course material which you can have access, or you can also Google and see LM317, you will get the data sheet, or otherwise I have given a link, just click on it, you will be able to see the data sheet. So the data sheet, if you see, so this is the data sheet of your 317. And here you have the main important features listed. Along with that is nothing but your applications are also given. So output voltage range adjustable, it's from 1.25 to 37. So that is what is given. Then you have your current, the output current greater than 1.5 ampere. And it also has all the protections. Now what are the applications of this 317? It has got a n number of applications. You can see here. This 317 can be useful for your say your DVRs. So it can be useful for your DVRs, desktop PC, then you have for your HVAC elements, hydraulic elements in your phones, then for say power bank solutions. So it has got n number of applications over here. Let's look at the electrical characteristics of this. There will be a short table which I want to show you. So here you have the recommended operating conditions. It is there in say the 5th page of your document where you have the recommended operating conditions. Are you able to see that? Here 7.3, okay. So what does it say is my output voltage range is minimum is 1.25 and maximum is 37. What should be the difference between the input and output? That is to say my Vi minus V0. So Vi minus V0, the input to output differential voltage, minimum can be 3 and maximum can be 40. Okay, so what do I mean by the differential voltage Vi minus V0? The voltage difference. Okay, so what happens that excess voltage which gets dropped across your IC, basically that is what is happening. So 1.25 is the minimum that I can give, and what is the output that I get? 37 is the output that I will be able to get. 1.25 is the minimum output, 37 is the maximum output. In the same way, the differential voltage, the difference between my input and output, minimum the difference should be equal to 3 and maximum the difference should be equal to 40. It can be, should be Allah, it can be equal to 40. Okay, so this we have to take care while we are designing the circuit and we are checking for the output. We have to take care the differential output minimum it should be equal to 3 as such. So let's take some example. I want an output of 6 volt. I want an output voltage of say 6 volt. What is the input that I can provide? What is the input that I can provide? I want an output of say 6 volt. So what is the input that I can provide? The difference between them, minimum it should be equal to 3 or maximum it can be equal to 40. 9. 9 or beyond that. Okay. So are you able to get that point? So the differential it should be equal to say 3 to 40. Next is the output current. Output current is nothing but minimum is 0.01, maximum is nothing but 1.5. Why we are specifying this current rating? I always say when I was discussing about 7805 also I told 1 ampere rating. Now I am telling it is 1.5. Why I am specifying the current rating quite often? Damage. So you should see to that all your components it is all within the current limit. Okay, so I should make sure if it is beyond, if I am making a circuit where I say I have a current of some 2 ampere and I am connecting this, then naturally my IC will get damaged. So I should make sure it is all within the current limits. So maximum this IC can handle up to say 1.5 ampere. Okay, so this table is essential, and then you have the operating junction temperature, which is say maximum it can operate till 125 degrees Celsius. So your pin diagram is essential. What should be the range of input? What should be the range of outputs? That is very essential when I am handling this regulator ICs. Clear with this? Any doubts? Why I am emphasizing on this is because one, you have an experiment, right? The other is we will be doing a project on regulated power supply. In that regulated power supply, we will be making use of this LM317 IC. Okay, 78405 you have handled now. Next, we will be making use of 317 in that particular project. Okay, so that time you should know how to handle the IC there. And you should know what will be my desired output. So minimum what could be the output that I will get? 1.25. Maximum it depends upon how I am going to program it. Okay, and current maximum it can handle till 1.5. So clear with this? Any doubts? Okay. So now we will move on to we have constructed with the half wave rectifier, then we have put a capacitor filter, then we have given a fixed voltage regulator, and then we have made a RPS basically. And of course we will also be doing a project where we will be making use of our bridge rectifier. So before that, let's learn the fundamentals of the full wave rectifiers that are there. Okay, because your entire course will be on this only, revolving around this power supplies. So full wave rectifier, you have got two types. One is center tap, another is your bridge rectifier. Center tapped and then the bridge rectifier. Now the transformers that you are having with you, it's all center tap transformer only. So now let's look into this. Center tapped, what's the working? So I'll have a step down transformer as such, maybe 15 or 12 volt rating. And to this, what do? We provide a diode. So this will be my circuit. Let's say I have D1 and this is going to be D2 and this will be my load resistor RL. So this comes from your AC mains. So this is basically your step down transformer. Okay, and I've provided the tapping over here. It means we are going to use the entire secondary. We are going to use the entire secondary of the transformer. For half wave rectifier, what did we do? We used only one half. We used only one half of it. Whereas here, we'll be using the entire secondary. Let's say if I have 15 volt rating, this will be 15, 0, and then I'll have a 15 over here. So this is my circuit diagram, basically. Okay. Now how this works, how this rectifier works. I provide a sinusoidal signal, right? And it is step down. So step down to say 15 to 20, step down to 15 VRMS. Now this is given as an input to my diodes, right? Let's say I take case 1. So case 1 is nothing but my positive half cycle. Positive half cycle of my signal. So what happens during the positive half cycle? I'll have say plus, minus, plus and minus. So what will happen? Diode D1 will conduct. D2 will be in the off state. Hope you are getting it, because positive I have it to the anode of diode D1. So it is forward bias. Whereas here in this case, negative is connected to the anode of the diode D2. So what happens? It is reverse biased. Okay. So case 1, when I give the positive half cycle, D1 is forward biased, right? So it conducts. D2 will be reverse biased. It doesn't conduct. So now what will be the direction of my current flow? It glows like this. It goes in this fashion. So I'll have a plus here and I'll have a minus here. So across RL will be my output V naught. Clear? So what do I get at the output? For the positive half, I get this portion. I get this portion of my signal. So this is the first case. So this fellow is short, whereas this D2 is open circuit. Clear? Now let's go to case 2. In case 2, what happens? First, what is my input in case 2? Negative half cycle. My input is negative half cycle of my signal. So when the negative half cycle of my signal comes, so let's take it in this fashion. So what will be the polarities as such? What will I have here? Negative half cycle. So minus plus. And this will be minus plus. Hope you got it, because you have the negative half there. Now what happens is, I have the diodes. Which diode will be biased now? D2 will be forward biased and your D1 will be reverse biased. So D2 is forward biased and your D1 is going to be reverse biased. So what will be the direction of the current flow now? D2 through RL. Okay. Now what is that you are able to see? Both the directions are the same. So across my load RL, I have my output created as this is the positive and this is going to be the negative as such. So what will happen here at the output point? I get the another half cycle. Right? So this is for my output because of my positive half cycle. This is the output which I obtained because of my negative half cycle. So this gets repeated. This is going to get repeated. So if I have a continuous waveform like this, I'll have this repeated in this fashion. Okay. So both your positive and negative half cycle are getting rectified in the center tap transformer. But what is the problem here? What could be the disadvantage if you go for this? It's rectified. Both your half cycles are no doubt rectified. Transformer designing, getting exact the tapping, it's very difficult. Okay, because it should be equally distributed. When I say 15, 15, 0, 15 andre, the upper half also should be 15 and the lower half should also be 15. So getting the exact tapping, it's very difficult. That's the main disadvantage. Okay, but efficiency wise, it is good. And if you see the ripple factor, for a half wave, what was the ripple factor? 1.21. Whereas when I go for this, if I'm not mistaken, it's 0.48. The ripple factor will be reduced. Okay, the ripple factor will be reduced if I go for the full wave rectification. So what do I mean if I say ripple factor is reduced? Pardon? The DC content is more. Your DC signal is high, whereas your AC ripples are reduced. So that is what I mean if I say my ripple factor is low if I go for the center tap transformers. Clear with that? When center tapped full wave rectifiers. So here both your half cycles are getting rectified in this. Any doubts? Now this is given as an input to my filter. Same thing. What filter we are going to use? A capacitor filter. So this will be given as an input to your filter and then you should be able to get the output as such. Any doubts? I'll show you in the manual also how that circuit is. Because you should be knowing what exactly is the content of your manual also. So halfway we have done. This is nothing but your center tap. So here if you see a rectifier, a full wave rectifier making use of your center tap transformer. So this is what we are doing here. And all the relevant equations are provided. And the tabulation, if you see, it remains the same like how we have done for the half wave. You have to note down your VP, VRMS and VDC, and then the theoretical calculations, the relevant formulas are also provided. Next is your bridge rectifier. This is your bridge rectifier. I request you to take down the diagram so that first take down this diagram. So when I am drawing, I will teach you how to position your diodes. So here you can see this D1 and D2 are in the same direction, whereas D3 and D4 will be in the same direction. So here also all the procedure, tabulation, everything is similar to that of what we have done for the half wave rectifier. Now let's see with the explanation part of this. So your full wave rectifier, in that what we are going to discuss now is a bridge rectifier. So you had your transformer, then what you have is your diodes. So what is the name of this diode? D1, D2, and this is D3 and my D4. Okay. So while you are drawing it, D1 and D2 will be in the same direction. D3 and D4 will be in the same direction. And here this is a crossover. It's not a junction. Okay. It's just a crossover. How do I connect the load? My load is connected across these 2 points. In some of the literatures, you also would have seen it connected like this. It's all one and the same. It's going to be across these 2 points. So this is just a crossover. So here it comes from AC mains, and then you have your output, say it could be your 15 or say 12, and then you get your output over here. So what do I get? I have this. I have the positive and then the negative half of my input. Now let's take the cases. Case 1, when I have the positive half cycle. So what is the polarity here? I have plus and then a minus. Okay, during my positive half cycle. So what happens to my diodes? Which two diodes are conducting? D1 and D3 is one answer. D1 and D2. You can see here D1 positive to the anode and D4 ge ಏನು ಹೋಗ್ತಾ ಇದೆ, it is reverse biased. So D1 is forward biased in the upper half. When I come to the lower half, I have a negative. Negative is given to D3. So what happens to D3? Reverse. Whereas negative goes to the cathode. So what happens to D2? Forward bias. So my D1 and D2 are going to be forward biased. D4 and D3 will be reverse biased. Any doubts in that? Are you clear, all of you? So D1 and D2 are forward biased. That is the reason I asked you to take down the diagram first. D3 and D4 are reverse biased. Now, how will be the direction of my current flow? Let's say I take this, it goes like this. So, D1, RL, like this. Back to this. This will be my current. So, what happens here? Entering is positive and this is going to be negative. I get my output voltage across my RL. I'll be getting the output voltage across my RL. So, the current direction is like this. Through D1, RL, D2 and back to the negative point of the neutral. Clear? So, closed. The circuit is closed as such. Now, coming to case 2. What happens in case 2? You get your negative half cycle. So, case 2 is negative half cycle. And what is the condition of my diodes? I have minus and plus. So, minus means what is the condition of D1? Reverse biased. D4? Forward biased. So, D4 is forward biased. D1 is reverse biased. So, this is forward biased, whereas this fellow is reverse biased. Now, coming to the lower half diodes. So, I have positive. So, what happens to my D2 and D3? D2 is reversed and D3 is forward biased. So, D2 is reversed and D3 is forward biased. So, what happens to the, how will be the current flow here? So, how will be the current flow in this case? D3, RL and then D4. I'll have D3, RL and then D4. I can just put another color. Okay. So, it comes like this. D3, RL and then to my D4. Okay. So, now also what's the drop? It is plus and minus. It's in the same direction, unidirection as such. So, what will be my output? This is for the positive half and this is for my negative half. So, this is going to be my rectified output. This will be the rectified output that I will get. Okay. And if you see whatever problems you had in center tap, it's eliminated here. But what is the problem that you will face here in bridge? More diodes. You have got 4 diodes because in center tap there were only 2. Whereas here you are having 4 diodes. So assembling 4 diodes, the 2 properly. You have to do it in a proper fashion. If you miss that anode and cathode, then you will not get the desired output. So assembling it, a number of diodes is also more. Okay, I am not going into the further details because that much is not required for the diploma students. This is enough. Construction wise it's difficult and the number of diodes that are involved is also 4 in number. Of course, this is also available as a module. You also have a bridge module. Okay, have you used it? No. Okay.
We had.
You had. Okay. So, bridge module is also available. That we have to just provide the input and check for the output. You will not have the trouble of connecting the diodes there. Okay, so but as of diploma students in their first year level, they should know how to connect it. In their project, probably they can make use of the bridge module. So please be aware, the bridge rectifier module is also available. So if at all they are assembling in any project, they can make use of the modules. But in the lab level, let them do it with the discrete components. Assemble with 4 diodes, may ask them to do the connections properly, and then you can get the desired output. Clear? So any doubts with respect to the working of this? Because generally this confusion comes. Which diode is forward biased, which is reverse biased? So while drawing, you make sure that D1 and D2 are in same direction, D4 and D3 are in the same direction. And how it should be? The cathode of this and then the anode of this. Okay, it both should not be anode. All that you have to make sure while drawing these diagrams. Clear? And the current flow you can show such that the output that is getting generated, it is in the same direction. So it is unidirectional what I get at the output. So if I aren't having any doubts, we can move on to the next. Okay. So as part of the experiment, half wave rectifier, then you also have your center tap, then you also have your bridge rectifier. You will be doing the same procedure, like say what we did in the rectifier experiment, we changed the load. We changed the load as say 5.6K or some 2.2K, then 1 kilo ohm. Then when we observed what is going to be my peak voltage, DC voltage, RMS voltage, and then we calculated what is going to be the ripple factor. The same exercise you will be doing it for the rectifiers, the full wave rectifiers also. But the filter and all that, it will be done, it was done for the half wave rectifiers. Okay, and all the calculations, what you did for the ripple factor, everything, it's an exercise included for the half wave rectifier. Clear with this part? Okay. Now I will just want to explain about the Zener regulators. I mean, first the Zener diodes basically, right? Because we have seen about the PN junction. Also, we should know about the Zener. Fine. So, first of all, what is your knowledge about Zener? What are Zener? What are Zener diodes? How is it different from our normal PN junction diode? For example, for the past 2 days, you had been using 1N4007, which I told you it's a rectifier diode. Okay. Now, we are terming one more called as the Zener diode. So, how is your Zener different from your normal PN junction diode? Its reverse breakdown voltage is low. For example, if we take our PN junction, we saw from the data sheet, it is very high. It's very high, say we had some 500 volt or 1000 volt if I take for 1N4007. Whereas my Zener diode, it will break down for less voltage. Say I have 6.2 volt, 6.8 volt, 9 volt, like that. It breaks for lesser voltages basically. Okay, so that is your Zener. But construction wise, how is it different from your normal PN junction diode? Construction wise, in which way it's different from your PN? It conducts in reverse direction, no doubt. It's all the same point. The reverse breakdown voltage is low, so it conducts in the reverse. Construction wise, what is the difference between your PN junction and then the Zener?
PN content is
Pardon?
content.
Which content?
Semiconductor.
It is heavily doped compared to that of my PN junction. Okay, your Zener diodes are heavily doped compared to that of the PN junction. Clear? So that's one main important feature of the Zener. Otherwise, that is also a diode. It has got anode and cathode. Why it should behave such that I can operate it in the reverse breakdown? In which way it is different from my normal PN junction diode? It's different because of the doping. Okay, so if I take my Zener diodes, they are basically heavily doped diodes. Okay. And what is the symbol of the Zener? Symbol of your Zener diode? Up and down?
Yes, that goes.
That is Z. Okay. It's like your Z. Fine. Same anode and cathode and Z. Clear? So that will be the symbol of it. Now, coming to the constructional diagram. I have my P, I have my N. So now when this P and N are brought together, what will I have here?
Depletion.
Depletion layer. I'll have what is called as my depletion layer. Now what will be the nature of this depletion layer in a Zener diode? It's heavily doped. So compared to your normal PN junction diode, how should be your depletion layer of the Zener diode? Thin. It should be thin. Okay, fine. So this depletion layer will be thin. Whereas in your normal PN junction diode, it will be wide. Whereas it will be narrow here, or it will be very thin. The reason, as it is heavily doped, you have large number of charge carriers. So they move. We saw when I have this P and N brought together, because of the charge imbalance, my charges will be moving from P to N and N to P. Okay, so they move very fast because I have lot of charge carriers available. So the number of ions that gets concentrated in the interface, it's going to be less as such. Okay, the number of ions that I have, this is nothing but my interface. This is nothing but my interface. The number of ions there will be less, which I term it as the depletion layer or your depletion region. So we saw in the previous class only, I'll have the hole. Associated with the hole will be what type of ions? Hole, and the associated ions will be electrons.
Positive.
I have the holes. Associated ions will be negative. Because I have a hole, it means it can be filled with an electron. When my atom gains an electron, it becomes a? When an atom gains an electron, it becomes a negative ion. Simple. I am gaining one negative charge. So I become negative ion. I donate one electron, or I say I lose one negative charge. So what do I become? Positive ion. That's it. Okay. So I'll have a negative ion, then I'll have a hole as such. And this side we have plenty of electrons. So electrons associated with positive ions. So biasing wise, it can be operated both in the forward bias as well as the reverse bias. So what can I do? If it is a forward bias, I will provide to the P positive and to the N negative. I'll provide the negative of my battery. Okay. So how will be the behavior of this?
Electrons lips from N to
This is forward bias basically. Okay. Let's make it clear. This is forward bias. So what will happen here? Electrons will move from N to P and holes will move from P to N. So if that is the case, the behavior is same as that of my normal PN junction diode. Okay. So if I plot it, say I have the forward voltage and then the forward current, reverse voltage, reverse current, Okay, the characteristics is same as that of my normal PN junction diode. Okay, and it will conduct for say 0.7 if it is a silicon and 0.3 ideally if it is going to be a germanium. Okay, so this is your cut-in voltage. Clear? Now coming to the reverse condition. Reverse, what should I do for the reverse? If it is reverse, what should I do? Oh, sorry. Sorry, I have erased everything. 1 second, I'll draw it. So I have a P, N, this is my depletion. So what should I do if it has to be a reverse bias? P should be given to negative and N should be given to positive. Okay. So now what should happen? What should happen in this case? Our depletion layer, keep in mind, it's a heavily doped diode. The depletion layer is going to be very, very thin. Okay, compared to our normal PN junction, the depletion layer here will be very, very thin as such. That's an important feature of this Zener diode. Now we have provided a negative bias. So what should happen here? What will happen? If it is a normal PN junction diode also, what will happen in the reverse bias? Pardon? What happens in the reverse bias?
Basically, in forward bias, where the electrons at holes, repulsion will happen. This reverse bias attraction.
Attraction of what? See, here I have negative. So what it will try to do? Attract the holes. Similarly, I have electrons here. What the positive of the battery will try to do? Attract the holes. So it widens. Basically, my depletion layer will widen. That is what we have seen in the normal PN junction diode also. It keeps on widening, and when my input voltage is going to be very much higher, then what happens? I have lot of electrons which goes and hits the nearby atom, and then it will in turn release electrons. So in that way, I'll have cumulative multiplication of the electron. And then the breakdown will occur, which we normally call it as the avalanche breakdown. So that avalanche breakdown is going to take place at say hundreds of volt or thousands of volt depending upon my diode specification. The same story here, but it is not the multiplication of electron. It is because of the high electric field that is going to be present. So how do I have a high electric field? Here I have this ions present, right? And my depletion layer is very, very thin. It's a narrow depletion layer, right? So now the electric field present there will help in the release of electron in the vicinity of it. Okay, you have a high electric field. How do I say my electric field is high? I think all of us know this relation. E is equal to V by L. If my length is less, what happens to my electric field there? It's more, right? We say this is a narrow depletion layer. So my length is less there. My length is less, naturally my electric field should be more. So that high electric field in the depletion region, it helps in the breaking of the atoms that are there in the vicinity. So if those atoms break, what happens? They release your electrons. So if the electrons are released, the vacancy caused because of the release of an electron is nothing but a hole. So in that way, I will have an electron and a hole created. Okay, so that leads to a breakdown of the device, which we call it as the Zener breakdown. So because of a high electric field that's created in your depletion layer, what happens? That helps in the breaking of the atom, which will release the electrons there in the vicinity. Right? So now I keep on increasing my reverse voltage. At one stage, what will happen? I will have lot of electrons and I will have a rapid current flow existing. So that is what we term it as the Zener breakdown mechanism. So there are two breakdown. One is avalanche breakdown and other is the Zener breakdown. Avalanche breakdown will occur in your normal PN junction diode to say at a very high voltage. And it is because of the cumulative multiplication of your electrons. Okay, whereas Zener breakdown occurs in your Zener diodes, or to say heavily doped diodes, and it is because of the presence of a very high electric field. Okay, that's the difference between both of them. And Zener, as you know, it will take for a lesser voltage itself. So that's how we get a 6.2 breakdown, 6.8 breakdown, or say 8 volt breakdown, like that. So when I look at the forward and then the reverse characteristics, forward we drew already. It's like this. Now coming to my reverse. So I'll have the characteristics in this fashion. Okay. So this voltage, it's nothing but my, instead of VB, we can give it as VZ, my Zener break. VZBR. This is my Zener breakdown. And the current here corresponding to that is your IZ minimum, and here I'll be having my IZ maximum. So irrespective of how I change my reverse voltage, what's happening? My current remains the constant. Of course, theoretically we say it is constant, but what happens to your current? There is a slight increase. Okay, there will be a slope associated with my curve. So my curve, if I exaggerate my curve, it will be like this. Slight slope associated, right? So this point where it breaks, it is called as your Zener breakdown. So first application, what we told was for the voltage regulator, which is the first fundamental component that can be useful for your regulation. Zener. That's what we listed. We told Zener, then we told transistor can be used, then we told fixed IC regulator, then we told I can go for an adjustable, then I can go for a SMPS. So the fundamental component that can be useful for my voltage regulation is nothing but my Zener diode. So what does it do? Irrespective of my variations in my reverse voltage, my current remains, when my current shoots up and my reverse breakdown voltage remains constant. So however I increase, I keep on increasing my VR. Once it has broken, what will happen? The current only will increase, but not my voltage. Clear as such? And here I have my breakdown. VZ breakdown has occurred. And the current corresponding to that is my Zener minimum current. And here I will be having my Zener maximum current. Okay. So this voltage we can determine if I'm using say FZ 6V2, then my diode will break at 6.2 voltage, or any other specification. Depending upon the specification, the breakdown voltage will change. So what is the thing that you have learned in Zener? Compared to your normal PN junction, what are all the differences? Heavily doped. Number one is heavily doped. Number two, it conducts in the reverse direction also. Depletion layer will be very, very thin compared to my normal. Why the depletion layer is thin? Because of heavily doped. Okay. Then
Avalanche breakdown, reverse
Depletion layer will widen a lot in your normal PN junction diode, but here because of your high electric field, what happens? The breakdown only will occur, which is called as your Zener breakdown mechanism. How the high electric field is created? Because of the thin depletion layer there. Clear? And what is the application? If I say a PN junction application is rectifiers, whereas for your Zener, voltage regulators. Voltage regulators, protection circuits, everywhere we can make use of this Zener regulators. Pardon? That is PN junction. PN junction, we can use it for clippers, clampers and all that. Whereas your Zener, for regulators, for protection circuits, you can make use of your Zener. Clear with that? So this is one experiment that we have. The characteristics of a Zener diode. And then the regulator part of it. So if you know the characteristics of Zener, of course you can handle the regulator part also. Okay.